Question 9.55. A car speeds over the top of a hill. If the radius of curvature of the hill at the top is 9 meter, how fast can the car be traveling and maintain constant contact with the ground? So let us first sketch the problem. Here I have the radius of curvature of the hill, which I will write as r to be equal to 9 meter. And we can draw a hill. The radius of this hill is 9 meter. And the car is on the top of the hill. We need to find with what speed can this car move so that it maintains constant contact with the ground. As the car passes over the top of the hill, it undergoes circular motion in vertical plane with the radius of the circular path as 9 meter. And the only force that provides the centripetal force required for this motion is the force due to gravity. The force due to gravity acts vertically down, and this is the force that is giving the required centripetal force to keep the car along the circular path. So we can equate force due to gravity Fg to be equal to the centripetal force Fc. Now we know force due to gravity is given as mass times acceleration due to gravity. And centripetal force I can write as mass times centripetal acceleration AC. We can cancel off the mass here, and then we get G to be equal to centripetal acceleration AC. Since we want to find how fast the car can be traveling, that is, we need to find the speed v. I will write my expression for centripetal acceleration in terms of speed v, which is v squared over r. Now I can rearrange the terms to write in terms of v. V squared will be equal to g times r. And when you take square root on both sides, you get v to be equal to square root g r. So this is the speed with which the car can travel and maintain constant contact with the ground. So let's calculate the value of v. V will be equal to square root. G is 9.81 and the radius r is 9 meter. And when you solve this, you get the value of v as 9.40 meter per second. So this is how fast that car can go on the top of the hill while maintaining constant contact with the ground. Question 9.20. A person rides on a Ferris wheel of radius r, which is rotating at constant angular velocity omega. Compare the normal forces of the seat pushing up on the person at point A to that at point B in the figure. Which force is greater, or are they the same? So here we have a Ferris wheel of radius r moving with constant angular velocity omega, and I need to compare the normal forces at two positions, at point A and point B. So let us first draw the free body diagram. I'm going to first consider point A. So for A, at point A, when I draw the free body diagram, I have the force due to gravity acting vertically down. So I will write this Fg. And then you have the normal force acting vertically up, perpendicular to the surface. Now, in case of Ferris wheel, if you notice, the cabins in which the passengers are seated is maintained such that the normal force at any point on the cabin is always pointing up. Because you're always vertically oriented while moving around the Ferris wheel, no matter where you're positioned. So the normal force at any point inside the cabin, the seat will always be pushing you up. The normal force will always be up. So at point A as well, my normal force due to the seat is acting up, whereas the force due to gravity is acting vertically down. The normal force here is used to overcome the force due to gravity as well as provide the required centripetal force to maintain the circular path. Centripetal force is acting towards the center of the circle, so it is in the same direction as the normal force. So I can write an expression for centripetal force Fc as the normal force minus force due to gravity. I will write the normal force N here as Na to indicate that this belongs to point A. Then we rearrange the term to write in terms of normal force. I will move Fg to the other side and we will get Na equals Fc plus Fg. Now the force due to gravity can be written as mass times acceleration due to gravity, as well as centripetal force Fc can be written as mass times centripetal acceleration AC. And since we are dealing with Ferris wheel moving with constant angular velocity omega, this centripetal acceleration AC I can write as r omega squared. So substitute that here in our expression for Na. I write Na equals mr omega squared plus m into g. And after you get this, we can take m as common, m, and write the expression as g plus r omega squared. So this is the expression for normal force at point A. Now we do the same thing at point. First, we identify the forces acting at point B. Again, we have the force due to gravity acting vertically down and the normal force perpendicular to the surface, which is up. But the only difference here is this time force due to gravity is in the direction of centripetal force. So you can calculate the centripetal force by taking a difference of the normal force and the force due to gravity. And since centripetal force is also acting down towards the center of the circle, we will take a negative sign for that. So I can write my centripetal acceleration for B. So this is for point B. Negative Fc is equal to normal for B minus Fg. Negative Fc because now again centripetal force in this situation is acting down towards the center of the circle. We rearrange the term again to write in terms of NB. So I get NB, move Fg to the other side, and when you do that, it becomes positive Fg minus Fc. Again, substitute for Fg and Fc as m into g and mr omega squared. So you get Nb equals mg minus mr omega squared. Take m as common out and you get g minus r omega squared. So this is the value of normal force at point B. Now the question is asking us to compare which force is greater or are they the same. So if you compare NA with NB, for NA you have mg plus r omega squared, whereas here it is mg minus r omega squared. So when we compare them, we can come to a conclusion that normal force at point A is greater than normal force at point B, because obviously here we are adding the two forces, the force due to gravity as well as the centripetal force. And here we are subtracting them. We are taking the difference of these two forces. So NA has to be greater than NB. Question 9.60. A particular Ferris wheel takes rider in a vertical circle of radius 9 meter once every 12.0 seconds. In part A of the question, we have to calculate the speed of the riders, assuming it to be constant. So let us first write down what the question has given us and then try to solve part A. I have the radius of the Ferris wheel, which is r equals 9.0 meter. And then we have that it completes one circle every 12 seconds. So I have the time period t, which is 12 seconds. I need to find the constant speed with which the riders are moving. So we need to find the speed v. Now we can calculate the speed v by taking the basic rule of speed, which is distance traveled over the time, since this is the constant value. And when we are moving along a circle, the distance that we travel d is equal to the circumference of the circle. And we can calculate the circumference by taking 2 pi r. So I will write the distance d as 2 pi r, and the time will be the time it takes to complete one revolution, which is t. So let's calculate v. It will become equal to 2 pi times the radius 9 divided by the time t 12. So when I solve this, I get the constant speed v with which we move to be equal to 4.71 meter per second. So this is the constant speed with which the rider moves when the Ferris wheel is of radius 9 meter and takes 12 seconds to complete one revolution. In part B, we need to draw a free body diagram for a rider at a time when she is at the bottom of the circle. Calculate the normal force exerted by the seat on the rider at that point in the ride. So here we need to draw a free body diagram when the rider is at the bottom of the circle. So at this point over here. So first force that we draw is the force due to gravity, which is acting vertically down, Fg. Now in a Ferris wheel, the cabins are always aligned in vertical fashion. So when we draw the normal force at any point on the cabin, the normal force is the force the seat exerts on the rider, and it will always be acting vertically up, perpendicular to the seat. So normal force here will be acting up like this, N. So this is the free body diagram for the rider. And we also need to calculate the normal force exerted by the seat on the rider. So let's start with the calculation for part B. If you notice, the normal force here at the bottom of the ride is used to overcome the force due to gravity, as well as it is used to provide the centripetal force required for the motion. So the net centripetal force you get at the bottom of the circle is equal to the normal force minus the force due to gravity. Because not all of the normal force is used for centripetal force, some of it is used to overcome the force due to gravity. And if you look at the direction of these forces, centripetal force is acting towards the center of the circle. So it will be going up, which is taken as positive. Normal also will be taken positive since it is pointing vertically up. Force due to gravity is acting down, so hence it is taken negative. Then we rearrange the terms to write in terms of normal force since we need to find this normal force. So I will write N is equal to Fc plus Fg. I move Fg to the other side, and when you move it, the minus sign here becomes plus. Now we can write Fc as mass times centripetal acceleration and Fg as mass times acceleration due to gravity. I need to find what is the relationship between centripetal acceleration AC and acceleration due to gravity G to solve further. Because I have to express this normal force in terms of mass times acceleration due to gravity. Now in part A, we had already calculated the value of speed v, which was 4.71 meter per second. I'm going to use this speed v to calculate the centripetal acceleration AC and then relate that acceleration to g. We know that AC in terms of linear speed v can be written as v squared over r. So I will calculate what is AC. AC will be 4.71 squared divided by r, which is the radius 9 meter. And when I calculate this AC, I get the value as 2.47 meter per second squared. I need to relate this centripetal acceleration to acceleration due to gravity. So I will find their relationship. I will take a ratio of AC over G. AC here we calculated as 2.47. Acceleration due to gravity is 9.81. And when you solve this, you get the ratio to be equivalent to 0.25. This means that my centripetal acceleration AC is 0.25 times the acceleration due to gravity. This is the relationship between them. So I'm going to substitute this value here in place of AC. So I can write for my N as, let's first take M common outside, AC plus G. Then I will write AC as 0.25 G plus G. Take G common out, write M 0.25 plus 1. Common outside G, when we take common outside, I'm in the when we take 5, in the second expression we are left with 1. And when you solve this, you get your normal force N to be equivalent to 1.25 mg. So this is my normal force at the bottom of the Ferris wheel or at the bottom of the ride. So this is my normal force at the bottom of the Ferris wheel or at the bottom of the ride. And if they give you the value of mass, you can calculate by substituting for M. In part C, they are asking you to perform the same analysis as in part B for a point at the top of the ride. So we are going to take a point on the top of the ride, which is here, and we are going to perform similar analysis as we did for part B and calculate the normal force. We first start with the force due to gravity acting vertically down, which is Fg. Then we have the normal force perpendicular to the surface, N. The difference here at the top is my centripetal force, Fc, is acting towards the center of the circle. So the direction of centripetal force Fc is downward. So here my force due to gravity is the one which is providing the centripetal acceleration required for circular motion. And this force due to gravity is acting opposite to the normal force. So when I write my expression for centripetal acceleration, I will take that Fc as negative because it is acting down, which is equal to the force of normal N minus Fg. Again, N positive because it is acting up, Fg is acting down. The centripetal acceleration in both cases is given as a difference between the normal force and the force due to gravity. The only difference here is on the top, Fc is acting in the same direction as Fg. Now to calculate the normal force, I will again move my Fg to the other side and we write the normal force N to be equivalent to Fg. When you move it to the other side, it becomes positive minus Fc. Again, we do the same thing. Fg is m into g minus m into AC. AC, as we found in the previous part, is equivalent to 0.25 times g. Let's substitute that. M times 0.25 times g. M into g is common in both terms, so I can take it out. When you take mg out here, you're left with 1 minus. When you take mg out here, you're left with 0.25. And when you solve this, you get the value of n to be equal to 1 minus 0.25 is 0.75 m into g. So if you compare part B to part C, you will notice in part B, the normal force at the bottom is equivalent to 1.25 mg, whereas the normal force on the top is 0.75 mg. So if you compare them, the normal force at the bottom is greater than the normal force at the top.